Hi, my name is Siddharth Joshi, and today I'll be speaking about data-efficient, contrastive, self-supervised learning. So let's start with what is data-efficient SSL and why do we care about it. In recent years, the volume of data generated has reached massive scales, and it will only keep growing at this rapid pace. However, to train ML models with supervised learning, we need labels, which are prohibitively costly at this scale. Thus, we rely on SSL where no labels are needed. But then training with SSL is typically 20 times more expensive than training with supervised learning. And that's where data efficient SSL comes in. If we can identify which examples from our large repository of data contribute the most to learning, we can train only on them and save huge amounts of compute. So why is data efficient SSL so challenging? Firstly, no prior work has characterized how important a given example is for self-supervised learning. Moreover, prior work in supervised learning uses the loss or gradient of examples, and this cannot be easily extended because in SSL, the gradient of every example depends on all other examples. In this work, we focused on contrastive SSL. So let's understand how it works before we dive into how to make it data efficient. Here we'll be using the popular info-NC loss used by SimCLR. Contrastive learning learns representations by relying on augmentations of the data. In particular, pulling augmentations from the same example closer together due to the numerator of the info-NC loss, and pushing augmentations of different examples further away due to the denominator. This ultimately results in semantically similar examples having their representations clustered together. So we can expect a cluster of dog representations and a separate cluster for cat representations. Now that we've understood contrastive learning, let's introduce the notion of expected augmentation distance, which will allow us to finally get to data efficient contrastive learning. Expected augmentation distance is defined as the distance between augmentations of two examples in data space. As we can see here, the augmentations of the two examples are very similar visually. The faces look similar and the paws look similar. Thus, we have small expected augmentation distance between x and x prime. Whereas in this example, the augmentations are not very similar, the faces and paws look very different, and hence we have large expected augmentation distance. So then, which examples contribute the most to contrastive learning? We show that examples that have small expected augmentation distance to the rest of their latent class contribute the most. Such subsets can be formalized by this objective, and this objective is submodular, which ensures that a greedy algorithm can find a near optimal subset extremely efficiently. Moreover, we provide a theoretical guarantee that shows that the downstream generalization performance of this subset is similar to that of the full data. As we see here, our method, which we name subsets that maximize augmentation similarity, or SAS, shown here by yellow lines, outperform random subsets significantly. In particular, we show that using SAS, 20% of CFAR 100, 40% of STL10, and 40% of TinyImageNet can be discarded without affecting downstream performance at all. In the full paper, we also extend these results to contrastive learning methods beyond SimCLR. Moreover, we find, perhaps surprisingly, that the most beneficial examples for supervised learning contribute the least to contrastive SSL. So, forgetting score is a measure of difficulty of examples for supervised learning. The most forgettable examples have been shown to be the most beneficial for supervised learning, but they contribute the least to contrastive SSL. If you look at the purple line, the most forgettable, these subsets perform significantly worse even than random subsets, and are in fact similar in performance to subsets that are the worst according to our objective, shown by the red line. So in summary, we can now use data efficient contrastive SSL to save lots of time and money when training on large amounts of data. Thank you so much for your time, and if you're interested in learning more about data efficient contrastive SSL, please visit our poster session, and you can follow me on Twitter for the time and venue.